everyone. In this video we look at the concept of chemical equilibrium and the idea of equilibrium constant. Now when we look at the chemical reactions, the rate of a chemical reaction is explained by a law which we call as law of mass action. Gullberg and Wage, they established a relation between the rate of a chemical reaction and concentration of the reactants or the partial pressure of the reactants in a form which we call as law of mass action. So basically the law of mass action is a relation that brings how the concentration of the reactants or the partial pressure of the reactants will be related to the rate of a chemical reaction. Now when we talk about rate of a chemical reaction, we will be able to understand more about it when we go to the idea of chemical kinetics, but here we may simply think of it as the rate at which the reactants in a chemical reaction are getting consumed, or we can also think of it as the rate at which the products are getting formed. Now the law of mass action is the rate at which a substance reacts is directly proportional to its active mass, and the rate of a chemical reaction is directly proportional to the product of active masses of the reactants. When we talk about one single substance which is undergoing the reaction, the rate of the reaction is proportional to the active mass, and when we talk about a reaction having multiple reactants, the rate of a chemical reaction is directly proportional to the product of active masses of the reactants, each active mass raised to the power which is equal to the corresponding stoichiometric coefficient which is appearing in the balanced chemical equation. Now we'll talk about what do you mean by the active mass. Here if you look at a sample equation where A moles of substance A, B moles of substance B are reacting to form C moles of substance C and D moles of substance D. Now over here the rate of the reaction, which we can see as the rate at which the reactants are getting consumed, will be proportional to the active mass of A. So here we are using this parenthesis notation to represent the active mass. So active mass of A to the power A. So each of the active masses are raised to the powers which are equal to the coefficients which are in the balanced equation, and the active mass of B raised to the power small b. So small b here is the coefficient here. Now we can convert this proportional relation into equation by introducing a constant. The constant k which we are keeping here, please keep in mind that we are using small k, and this will be called as the rate constant or velocity constant of the reaction at a given temperature. This will be depending upon the temperature. Now here when we talk about the active mass may be representing concentration of the substances, or it may even be representing the partial pressure of the substances. So here if we talk about generally the reactions where we have substances in liquid solution, we will be looking at the concentrations, and when we talk about reactions predominantly involving gases, we will be looking at the partial pressures of the gases. So this is what is the law of mass action. The law of mass action basically relates how the rate of a reaction will be linked to the active masses of the reactants. Now when we say active masses, we may be referring to the concentration or we may be referring to the partial pressures. Now we'll study more about this law of mass action in chemical kinetics, but the reason why we are trying to take an introduction to this is we need to understand that the rate of the chemical reaction, so if you think of it, the rate at which the reactants are getting consumed or the rate at which the products are getting formed, it will depend upon either the concentration values or the partial pressure of the reactant. Means if the concentrations or partial pressures of the reactants are more, then the rate of the reaction will be more, and if it is less, then usually the rate of the reaction will be less. Now when we look at the idea of equilibrium, so if we take this sample reaction where the substance A is reacting with substance B to produce substance T and substance D. Let us say T is equal to 0, we are starting with initial amounts A0 and B0, and let us consider that initially there is no C or there is no D. Now as time progresses, what we would observe is the reactant amount will be getting decreased and the product amount will be getting increased. So if we try to look at how the concentrations, so when we say concentration, we are looking at the molar concentration, which is given by the number of moles of the substance present in 1 liter. The concentrations of the products, as we can see, they will be increasing with respect to time, and the concentrations of the reactants, they will be decreasing with respect to time. Now up to what level they would decrease or up to what level the product concentrations will increase would depend upon how we will achieve the equilibrium. Already in the previous video we talked about the classification of the reactions into 3 types, where by the time we reach equilibrium, in the 3 cases, in one case we'll have predominantly the product getting formed, in other case we have predominantly the reactant itself left over, in the third case we'll be having considerable amount of both reactant as well as the product. Now as we reach this equilibrium stage, the product concentration as well as the reactant concentration will not be changing henceforth. So this is what we call as the equilibrium stage. Now when we try to understand this from the rate of a chemical reaction point of view, if you look at the forward reaction, I'm looking at the rate of the forward reaction. So forward reaction, here we are referring to A plus B combining to give you C and D. Now the forward reaction rate will depend upon the concentration of A and concentration of B. As per the law of mass action, what we will be able to see is the rate of the forward reaction will be proportional to the active mass. So here we are representing the active mass in terms of the concentration of A power 1 and concentration of B power 1. So as the time progresses, what is happening here is the amount of A and amount of B are decreasing. So thereby the rate of forward reaction will keep decreasing. And if you see the other side of the story, which is C plus D combining to give A and B back, this is what we call as the reverse. So the reverse reaction, if you look at it, for the reverse reaction, reactants will be C and D. So here, as per the law of mass action, what we'll say is rate is proportional to the concentration of C into concentration of D. Now as time progresses, we'll be forming more and more amounts of C and D, so thereby the rate of the backward reaction or the reverse reaction will be increasing, and we will eventually reach a stage where the rate of the forward reaction is equal to rate of the backward reaction. Now at that stage, the rate at which the reactants A and B are getting consumed will be equal to the rate at which they are formed back because of the backward reaction. And this is the reason why we represent every chemical reaction which is undergoing equilibrium with a double-headed arrow. And this is what is the idea of reaching an equilibrium stage. Now when we talk about the properties of the equilibrium, the first and important property of the equilibrium is that it is a dynamic phenomena, which means once we reach equilibrium, it is not like the forward reaction and backward reaction or the reverse reaction are stopping, but they would happen at the same rate. And the observable properties of the system, so when we talk about system, we are referring to the entire reaction mixture, such as pressure, concentration, density, all of them, even color and some of the other properties, all of them will remain invariant with time, which means they will be remaining constant with respect to time. So henceforth, once we reach this equilibrium stage, the composition, properties, everything about the reaction mixture are going to remain same. And the other important aspect about the chemical equilibrium is that it can be approached from either side, which means if we begin with A and B as per this reaction, we will be able to form some amount of C and some amount of D by the time we reach equilibrium, which means we are reaching equilibrium starting from A and B. The same time, if we start with C and D, again we will see that there will be some amount of A and B getting formed and we will be reaching the equilibrium. So this is the properties or the important aspects related to the idea of equilibrium. Now the chemical equilibria can be classified into broadly 2 categories. One is what we call as homogeneous. Homogeneous would mean that the reaction which is undergoing this equilibrium will have all the reactants and products in the same phase. So we'll look at the examples. H2 gas plus I2 gas gives rise to HI gas. Nitrogen gas plus hydrogen gas gives rise to ammonia gas. N2O4 gas on dissociation gives NO2 gas. Acetic acid and ethyl alcohol, they combine to give ester and water. So the last one is in the liquid phase. The first three examples are in the gas phase and the last one is in the liquid phase. So such type of equilibria we call them as homogeneous equilibria. The other one is heterogeneous equilibrium. Now this will be happening when the reactants and products are having different phases. Now if you take the dissociation of limestone, which is calcium carbonate, it will be giving us calcium oxide, which will also be a solid because calcium carbonate will be a solid, and CO2 gas. So here we see that we have both solids as well as gas. And second one, NH4HS, which is a solid, on dissociation will give us ammonia gas and H2S gas. So this also will be involving solid as well as gas phases. The third example, NH2CO2NH4, which is a solid, on dissociation gives us ammonia gas and then CO2 gas. So this also is involving both solids and gases. So all these equilibrium that we talked about will involve more than one phase, and hence we'll be categorizing them as heterogeneous equilibrium. Now law of chemical equilibrium basically determines how we will be able to study the idea of equilibrium. So the idea of equilibrium qualitatively is understood as a state where we will reach, after which no more change in the concentrations or the amounts rather of substances will be noticed. Now to put it in a quantitative manner, to deal with the equilibrium on quantitative aspects, we have law of chemical equilibrium. Now according to this law, the ratio of product of active mass of the products to the product of active mass of the reactants, which means the active mass of the product substances will be in the numerator and active mass of the reactant substances will be in the denominator, with each of these terms raised to the power of its coefficient in a given chemical equation, which means each of these active mass values are raised to the same powers, that of the coefficients which are present in the given chemical equation, and this ratio will be a constant quantity at a given temperature, and this constant is called as equilibrium constant. So the law of chemical equilibrium tries to quantify the idea of equilibrium by using a concept of equilibrium constant. So if we were to understand this with an example, let us say we have A moles of A combining with B moles of B to give C moles of C and D moles of D. Now for this type of reaction, if we were to express the equilibrium constant is generally represented by the symbol capital K. It will be equal to the active mass of the products. Now we are using parenthesis notation to represent the active mass of the product C raised to the power C, because the coefficient here is C. Active mass of the product D raised to the power small d, so small d is the coefficient over here, divided by the active mass of the reactants. A is one reactant raised to the power small a, which is its coefficient, and B is another reactant raised to the power small b, which is its coefficient. And this term is what we are calling as the equilibrium constant, which will be a function of temperature, and this will be representing quantitatively the relation between the active mass of the reactants and active mass of the products at the stage of equilibrium. Now already we have discussed about it. The active mass can be measured either in terms of the concentration, the molar concentration, moles per liter, or it can even be measured in terms of the partial pressures of the gases, which will be in the pressure unit, maybe atm or Pascal, etc. Sometimes we may even use bar. So this is about the idea of chemical equilibrium. Now if we were to give the equilibrium constant formula for any of the specific examples, let us say we have nitrogen gas combining with hydrogen gas to produce ammonia gas. So this is the given equation. Now for this equation, the equilibrium constant, which will relate to the active mass of the product. So product here is ammonia, so within parenthesis we'll keep ammonia, power 2 because the coefficient here is 2, divided by reactants are nitrogen gas, active mass of nitrogen gas. So the active mass of nitrogen gas, the power is 1 because the coefficient here is 1, and the active mass of hydrogen power will be 3 because the coefficient here is 3. So this represents the equilibrium constants for the reaction where nitrogen gas and hydrogen gas are combining to form ammonia gas. So this is about the law of chemical equilibrium. Now we can define the law of chemical equilibrium by using the idea of law of mass action. So if we take this sample reaction where A moles of A are combining with B moles of B to produce C moles of C and D moles of D, as per the law of mass action, if we look at the forward reaction, so forward reaction would mean A and B combining to give C and D. So for the forward reaction, rate will be equal to rate constant. So here we are referring to the forward reaction, so we'll use rate constant for the forward reaction Kf into the active mass of A power A, active mass of B power B. Similarly, for the backward reaction or the reverse reaction, rate will be equal to Kb. So this is the rate constant or velocity constant for the backward reaction. So backward reaction would mean C and D combining to give A and B back. So the reverse reaction, law of mass action will give us the rate to be Kb into concentration of C power small c into concentration of D power small d. So here we may be representing the active mass as a concentration, or we may be representing it as partial pressure. So here we'll just go with the idea of active mass. Now when we talk about the idea of equilibrium being reached, the rate of forward reaction, as we already seen, forward reaction rate will decrease with time, and the reverse reaction rate will increase with time. Eventually we'll reach a stage where the forward reaction rate is equal to the reverse reaction rate, and that is what will be the equilibrium. So which means once we reach equilibrium, the rate of forward reaction is equal to rate of backward reaction. So what we have is Kf into active mass of A power A into active mass of B power B is equal to Kb into active mass of C power C into active mass of D power D. Now when we take a ratio of Kf by Kb, the forward rate constant by backward rate constant, so this A power A and B power B will go to the other side, they will go to the denominator. So what we have is active mass of C power C into active mass of D power D by active mass of A power A into active mass of B power B. And already we talked about the property of rate constant or velocity constant. So rate constant or velocity constant for a given chemical reaction will be a function of temperature, which means both Kf value and Kb value, they are a function of temperature for the given chemical reactions. So Kf will be for the forward reaction and Kb will be for the backward reaction, and this will be always a constant at a given temperature, and this is what we are calling as equilibrium constant K. So in other words, we can also look at the equilibrium constant K as the rate constant for the forward reaction by rate constant for the backward reaction. So this is about the idea of law of chemical equilibrium. Now when we take the active mass to be representing the concentration, the corresponding equilibrium constant, we denote this as Kc, and this is what we call as equilibrium constant expressed in terms of concentration, equilibrium constant expressed in terms of the concentrations. So the unit of this Kc will be generally in terms of moles per liter. So it will not be mole per liter, it will be in terms of moles per liter, and we'll talk more about it because each of the concentration terms will be mole per liter, and the powers will keep changing from equation to equation, which would mean that Kc would not have a fixed unit. but it will be generally in terms of moles per liter. And if we are representing the active mass with the partial pressure, which we do in the case of mainly the gas phase reaction, the equilibrium constant will be denoted as Kp, which is equilibrium constant expressed in terms of the partial pressures, and for this the unit will be in the pressure unit. So it will not be exactly pressure, it will be in terms of the pressure. So it may be expressed in terms of pascals, or it may be expressed in terms of ATMs, or it may be expressed in terms of bar. Now it is interesting to note that in the beginning or the early stages of study of chemical reactions, most of the times the pressure of the gases used to be measured in bar, which means if we just give a value of Kp without mentioning the unit, then we take it to be representing the Kp value in bar, because that is how conventionally the pressures of the gases involved in chemical reactions used to be measured. So we'll take a look at it again in the subsequent videos, but this is about the idea of two equilibrium constants that we'll be using, mainly Kc and Kp. Of course, it is not like we have only two equilibrium constants. There are also other equilibrium constants that are beyond our purview here, like we may have K chi. So chi represents mole fraction, where we can talk about the relation between the mole fractions of the product substances and mole fractions of the reactant substances. So here in our purview we'll be mainly focusing on the equilibrium constant measured with respect to the concentration Kc, and equilibrium constant measured with respect to the partial pressure Kp. So this is the idea of equilibrium constants.